Welcome, probability people. Up until now, we've entirely been talking about probabilities, essentially the chance that a statement is either true or false of a random variable. And it turns out that's going to allow us to extend our notion of probability. The average, which is also called the mean of a random variable. And to think about what's going on with these random variables, what I want to do is just think about rolling six-sided dice. So here I'll do this in order: green, purple, blue. So I got a 2, a 1, and a 5. If I roll again, I get a 1, a 6, sorry, a 4, and a 6. If I roll again, I get a 3, a 4, and a 5. And I could, of course, keep doing that an unlimited number of times. So the question is, if I keep doing that, if I keep rolling independently, IID, this six-sided die, pull my bookmark out here, then what happens when I average this? Okay. So what happens when I take 2 plus 1 plus 5 plus 1 plus 4? Those are the first 5 numbers, and divide by 5. That's called the sample average of the numbers. And we get 2 plus 1 is 3, plus 5 is 8, plus 1 is 9, plus 4 is 13. So this is 13 fifths, or 2.6. What if I kept going? What if I took those numbers and then added in the next 4 numbers? Plus 6, plus 3, plus 4, plus 5. So let me do one more just to make it 10 numbers. Plus 3. We were at 13, so 19, 22, 26, 31, 34. So now we're at 3.4 for our sample average. And a natural question to ask is, does the limit exist? So as I sample more and more things, will the sample average converge? And that was one of the most important questions in early probability theory. People wanted to know what would happen as I took more and more tries of this particular random variable. What's going to happen as the number of tries goes to infinity? Well, in order to answer that question, let's think about the outcomes. So the outcomes, I know, have a 1/6 chance of being 1, and a 1/6 chance of being 2, and a 1/6 chance of being 3, a 1/6 chance of being 4, a 1/6 chance of being 5, and a 1/6 chance of being 6. So I can ask the question, if I try, let's say 6 million times, about how many 1s, 2s, 3s, 4s, 5s, and 6s do I have? Hopefully it's not too much of a stretch to say that if I have a 1/6 chance of getting a 1 and I roll my die 6 million times, that roughly speaking, I'm going to have a 1 in 6 chance of getting a 1. And so roughly 1 million of those 1s, so roughly 1/6 of those 6 million tries, or about 1 million, will be 1s. And about a million will be 2, and so on, up to about a million will be 6. Okay, so that's telling us inside our sample average. So for our particular sample average, we've got about a million that are 1s. We've got about a million that are 2s, and so on, up to about a million that are 6s. And all of that is divided by 6 times 10 to the 6th. So the fact that we were working with a million cancels out. We could have been working with 6 billion, we could have been working with 6 trillion, so on. No matter how large that number is, it's going to cancel out. And we're going to be left with 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3 plus 1/6 times 4 plus 1/6 times 5 plus 1/6 times 6. And so as our sample average gets large, as we take more and more samples, we get closer to 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3 plus 1/6 times 4 plus 1/6 times 5 plus 1/6 times 6. Now I'm going to do a speed calculation and say that that is 3.5. Later on, we'll talk about how I did that so fast. There's a trick. I didn't add up all the numbers and divide by 6. There's a shortcut that we can use to do problems like that. If I have a die that is showing the numbers 1 through 6 on it, and I ask, what's the average number to come out of that die? 3.5, well, doesn't seem like such a bad pick for the average of those numbers. Now, I should note, of course, that is not one of the values that the die actually takes on. It's not in the set 1 through 6. And that's because the average of value of these numbers doesn't have to be one of those numbers. It can fall in between, exactly as it does here. Always in mathematics, we have a choice. Do we try and prove that something is true, or do we just define it and then see what the consequences are? And in this case, we're going to take the latter approach. So all of that was motivational. Suppose that I have a discrete random variable. So the probability that the random variable is either little x1 or little x2 or so on. Actually, let's do just finite to start. So the probability that x falls in the set little x1 up through little x1 equals 1. Then the expected value, which is also known as the expectation. It's such an important concept that we give it at least 4 different names. The expectation, also known as the mean, also known as the average of x, is defined to be the sum as I goes from 1 up to n of the value that the random variable takes on times the probability that it takes on that value. The notation that we'll use is a blackboard boldface E applied to the random variable. So the expected value of the random variable x is going to be defined. We sum over the values that the random variable takes on times the probability that it takes on those values. Story example in the chapter, we have an amount of taxes. Each person is paying either 5, 2, or 1 in taxes each year. And the probability that t is 5 is 0.1. The probability t is 2 is 0.4. And the probability that t equals 1 is 0.5. So if I asked you for that particular random variable, what's the expected value of t? Well, you would take the value that it takes on, 5, times the probability it takes on that value, plus the value that it takes on 2, times the probability that it takes on that value, plus the value that it takes on, which is 1, times the probability that it takes on that value. So we get 0.5 plus 0.8 plus 0.5, or 1.800. And that's another example, of course, of a random variable whose average value, whose mean, whose expectation, whose expected value doesn't actually equal any of the values that it takes on. One thing that I want to notice is that this expands the idea of probability. In other words, probabilities can only lie between 0 and 1. Expectations can be bigger than 1. Turns out they can be negative. They can do all sorts of things. But to be an extension of probability, they have to include probability as a special case. And they do. Here's the following fact. For S an event, the mean of the indicator of that event is the probability of the event. Why is that? Well, an indicator function is either 0 or 1, which means that the expected value of the indicator of the event is 0 times the probability that the indicator equals 0, plus 1 times the probability that the indicator equals 1. But the indicator equals 1 is the same as saying S is true. So this is just saying the probability of S. Now remember, we have a name for these indicator random variables. We also call them Bernoulli random variables. And so this is another way to say this statement is that the mean of a Bernoulli random variable is the probability that the event inside the random variable occurs. So we could have entitled this course Expectations or Averages because they include probabilities as a special case. That being said, it generally works better if we teach about probabilities first and all the properties of probabilities instead of just including them as special cases of the expectations. But that being said, once we have the properties of expectations, we can derive all of our probability properties simply by looking at them as the mean of indicator random variables. Okay, any questions about that? So this works well, and this argument, hopefully, that I gave at the beginning makes sense when we're talking about discrete random variables. What about when we're talking about continuous random variables? So what about expectation of continuous random variables? Well, the idea, it turns out, stays the same. So first, let me just think about countably infinite random variables. So definition. If probability that X is in now the sequence X1, X2, and so on with probability 1, then the expected value of X is the sum as I goes from 1 to infinity of X sub I times the probability that X equals little x sub I. But we run into a problem. We know that these infinite sums are in fact limits, and limits, unfortunately, don't always exist. So we only say that this is true when this limit exists. Otherwise, we have a variable which is not defined. When expected value of x exists, we call the random variable integrable. Now, unfortunately, not all random variables are integrable. Some of them, this limit goes to infinity. Some of them can be set up so that limit doesn't exist at all. And we'll see an example of that in a minute. It's a little easier to do in the continuous framework. So first, I'm going to do the continuous. But before we get to that, let me just state the following fact. W is integrable if and only if the expected value of the absolute value of W is finite. Some of you may remember from your calculus or real analysis classes that the sum of a positive set of things or non-negative set of things is either finite or infinite. Those are the only two possibilities. And in fact, I'm saying that if we sum up using the absolute value of the random variable W, if it's finite, the original variable is integrable. If it's infinite, the original variable is not. Let me just point out, this follows from the things that we've said so far, but I just want to make sure that everybody has this simple but important fact under their belts. If the probability that x is in a finite set of numbers is 1, then x is integrable. So anything like rolling dice or the taxes example that I talked about earlier, because we only had a finite number of things in our sum, we never have to worry about the limit not existing. So because we only have a finite number of things in our sum, we're 100% positive that the random variable has a mean. The next thing that I want to do is talk about the sample average. What's going on with that sample average? Typically, we're interested in it for an IID sequence of random variables. So say that x1 through x2 are IID x, where the expected value of x exists. So we're thinking about x being an integrable random variable. Then for each n, we have a sample average, which is to take the first n entries in that sequence, add them up, and divide by n. What can happen? Well, it could be that that sequence doesn't converge. So does this converge as n goes to infinity? And it turns out, for instance, if my x sub I are between 1 and 6, this sample average might not converge. It might be that I start off with a 1, and then a 1, and then a 1, and then a 1, and I get a bunch of 1s, and then I get a bunch of 6s, say twice as many 6s as I did 1s. So if I get I 1s, then I get 2I 6s, then I get 4I 1s, and that pattern keeps repeating. So each time I get twice as many things pulling it in the opposite direction as I did before. So if you look at that sample average, it's not going to converge because it starts off at 1, and then it gets pulled to about 4 by those 6s. Then it gets pulled back below 2 by those 1s. Then it gets pulled back above 4 by those 6s, and it keeps bouncing back and forth instead of converging. But of course, when you roll a die, what's the chance that this happens? 0. The chance that you actually roll all 1s, then all 6s, then all 1s in this particular pattern, it's 0. But you may wonder, well, aren't there a lot of patterns that could lead to this thing not converging? It's true. There are actually uncountably many patterns that lead to that not converging. But the chance that any of those patterns occur is 0. So even though you're not guaranteed that this will converge, the probability that it converges will equal 1. And that's called the strong law of large numbers. So let's see what it says. It says given x1, x2, and so on, IID as x, where x is integrable. If I look at the limit as n goes to infinity of the sample average of the first n things, the probability that that limit will be the expected value of x equals 1. And that was the first great theorem of probability. That's when probability started to get more respect as a mathematical subject. Because up until that point, we didn't really know this fundamental thing about random variables, that they converged to their expected value. And after that, we did. Now, I want to point out, because many of you have had statistics and know about things such as variance that we're not going to talk about until later in this course, variance doesn't appear here. So you can have a random variable that has an expected value, but an infinite variance, and the strong law of large numbers is still going to work. So the strong law of large numbers does not depend on having a variance. It does need an R in the word strong. So most probabilists like to abbreviate that. So I don't actually write out the word strong too often. Apparently it takes me 2 tries to spell it correctly, but there you are. So that is a super powerful idea, and we get a lot of extra things for free from that idea. So let me just remind you, in case you forgot your limits from Calculus 2, that if I take the limit as n goes to infinity of a times f of n plus b times g of n, that's going to be a times the limit as n goes to infinity of f of n plus b times the limit as n goes to infinity of g of n, as long as the limits exist. We always have to put that, that caveat on things. As long as our limits exist, we know what our limits are going to be. Well, what does that tell us about expectation? It tells us because the expected value can be thought of as a limit, it's going to obey this same sort of behavior. Now, other things obey that behavior too. You may recall derivatives have that sort of behavior. The derivative of AF plus BG equals A times derivative of F plus B times derivative of G, and so on. So it's not the only type of mathematical object where this sort of behavior occurs. So we give it a name. Definition. Say that script L is a linear operator if for all vectors v and w and scalars a and b, the linear operator applied to AV plus BW is the same as A times the linear operator applied to V plus B times the linear operator applied to W. And so an example of that is the linear operator that applies to sequences, which is the limit as n goes to infinity. That is a linear operator. So example, linear operator equals limit as n goes to infinity is a linear operator. And because of the strong law of large numbers, the expected value inherits that linear operator property. So because of the strong law of large numbers, we have the following fact. Expectation is a linear operator. When I talk about expectation being a linear operator, people are worried, does this apply to dependent random variables? And the answer is yes. Note that in this limit here, suppose that G was twice the value of F. Well, this statement still holds, even if G depends very strongly on F. In the same way, this holds whether or not the variables are independent. So let me give an example of that. Suppose that X is a D6, Y is a D6, W is 7 minus X. Okay, well, let's think about that. If X is 4, W is 3. If X is 6, W is 1. If I take 7 and subtract a number from 1 through 6, that number will still be from 1 through 6. And so this will still be the distribution D6. So now suppose that I take the expected value of X plus Y. Well, I said that expected value was a linear operator. So just like derivatives, just like integrals, just like limits, you can distribute over the plus sign. So this is the expected value of X plus the expected value of Y. But those two have the same distribution, which means that they have to have the same expected value, because the expected value was just defined in terms of probabilities. And the probabilities and outcomes for X and Y are exactly the same. So this is twice the expected value of X. What about the expected value of X plus W? Well, that's also the expected value of X plus the expected value of W. It doesn't matter that W is some function of X. All that matters is that they are two random variables. And again, because X and W have the same distribution, they're both rolls of a six-sided die, that is just going to be twice the expected value of X. But now suppose that inside this W, inside this expectation, I say what W is. W is 7 minus X. Well, our algebra teachers would be proud if we could simplify X plus 7 minus X to just be expected value of 7. The plus X and the minus X cancel out. And this is asking, what is the average value of a random variable, which is always 7? And the answer, 7. So if we follow our chains of equals all the way across, we get that 7 is twice the expected value of X. Since 7 is twice the expected value of X, the expected value of X is 7 halves, or 3.5. That allows us to find the expected value of any die roll. So here's a fact. The expected value of X, where X is a roll of a die with n sides, is 1 plus n over 2. So if I roll an 8-sided die, do I have an 8-sided die? Oh yeah, there's one. So if y is an 8-sided die, the expected value of y is 1 plus 8 over 2, or 4.5. Notice that when I graph that, I've got 1, 2, 3, 4, 5, 6, 7, 8. Okay. 4.5 lies right there. And one way to think about the expected value from a physical point of view is if I look at the PDF of this random variable and I carve it out of wood. So if I put up a little chunk of wood that was 1/8 high at 1, 2, 3, 4, 5, 6, 7, 8, then the expected value of y is the balance point for the PDF. So if, in other words, if I took this thing and carved it out of wood, this histogram, this PDF for y, the expected value would exactly be the fulcrum, the place where you would put the middle of your seesaw so that your seesaw stayed level and didn't tip. So that's an interesting connection between probability and physics. In physics, these sorts of rotations are called moments. And so the expected value of a random variable is also sometimes called the first moment of the random variable. So what's another way that I know that that balance point has to be in the middle? Well, it's because I have symmetry. So I have a symmetry around 4.5. If I look at the PDF to the right of 4.5, it looks exactly like the PDF to the left of 0.45. And so we're going to make the following definition. Say random variable x is symmetric around m if x minus m and negative x minus m have the same distribution. So what am I doing when I subtract m from x? Well, I'm sort of sliding things over to 0. And then I'm saying, if I can flip things over around 0 and I have the same distribution, then I have symmetry. And one of the nice things about symmetry is that if your random variable is symmetric about m, so if x is symmetric about m and is integrable, then the expected value of x equals m. And the proof is essentially what we did with the dice earlier. So recall, note, that the expected value of x minus m, we're saying that x minus m has the same distribution as minus x minus m. So they've got to have the same expected value as well. And so that means if I bring this over to the other side, minus expected value of minus x minus m equals 0. But linearity of expectation tells me that I can bring negative signs inside. And so those two negatives cancel each other out. So the expected value of x minus m plus the expected value of x minus m equals 0. This first part is just the expected value of x minus m, because I just, again, expected value of a constant is just the constant. The second part is expected value of x minus m. And so we get twice the expected value of x minus 2m equals 0. or solving for the expected value of x, we just get m. Oh, and this is a fact. I put my parenthesis in the wrong spot. That actually makes sense now, hopefully. Okay, so let me just, to get this linearity stuff in your head, let me just do a couple more examples. Suppose that the expected value of x equals 3 and the expected value of y equals -1. And I ask, what's the expected value of 3x minus 4y? And all linearity of expectation says is do this thing the same way that you do a derivative or an integral. This is 3 times the expected value of x minus 4 times the expected value of y. And now we know that expected value of x is 3. And the expected value of y is -1. And so we end up at 7. Now, the last thing that I want to do is I want to talk about writing sums as integrals. And so the idea here is, recall that integrals with respect to counting measure are sums. So if I want to sum over little a in big A of f of little a, that is an integral with respect to counting measure of f of a. If I'm looking at the expected value of a random variable, which is the sum over values x of x times the probability that big X equals little x, and that's the sum over all possible values of x, so all real numbers, that's the same as the integral over x, all real numbers, of x times the probability that x equals little x with respect to counting measure. Now remember that this is the probability that x is in a little differential element around x, where our differential uses counting measure. So why am I bringing this up now? Well, this gives us an idea of how we can express our expected value when we're doing it not with respect to counting measure, but when we do it with respect to Lebesgue measure. So for Lebesgue measure, the expected value of x is the integral. I wrote x in big X here, but I should have written x in the real numbers. Sorry about that. Is the integral over x in the real numbers of x times the probability that big X is in dx, but now we're doing Lebesgue measure instead of counting measure. And another way to say that is it's the integral over x of x times the density of the random variable at little x dx. And the great thing, the wonderful thing about this setup is that the strong law of large numbers, the linearity of expectation, everything that I talked about symmetry, still holds for continuous random variables as well as discrete random variables. So with this definition, with this idea of integrals being sums with respect to counting measure and Riemannian integrals with respect to Lebesgue measure, we can write the expected value of x regardless of whether we're dealing with a continuous or a discrete random variable. So that's kind of nice.